Hello and welcome to Study Unit 7 of the 9 study units of this module. Yes, we are nearing the end and I have to say the worst is over. Now it's only enjoyable. Sorting is a very important topic in any computer science course. Sorting is all to do with sorting an array of typically numbers, figuring out different strategies to sort numbers. Now, there are 4 or 5 strategies, there are many more, but there are 5 that we are going to do. For each of those, you should be able to draw the diagram and explain in detail how a given sequence of numbers are sorted. So we will ask you, for example, indicate on a diagram and with explanation how merge sort will sort the following list of numbers, or how quicksort will sort the following numbers. This is typically 10 plus marks in the exam. So if you can do this, you can tick 10 marks in the exam. So once again, what's your aim? Your aim is to be able to draw a diagram to indicate how a certain strategy or algorithm will sort given numbers. We are going to do 5 strategies: insertion, bubble, merge, quick, and bucket sort. Now we have done bucket sort from study unit 2, and bubble sort you've done before, and we have done the basics of insertion sort because we did a method called insert sorted. Quick sort works with recursion, and merge sort has merging as a major component, so that's why we did merge when we previously did merge. So why do we study sorting? There are 3 main reasons. Sorting algorithms contains many good, clever, creative problem-solving techniques so that you can get ideas. And then it also creates more opportunity to practice the basic stuff, ifs, whiles, repetition, and so forth. And you can also see the difference in sorting times when you do sorting algorithms. Okay, so we are going to make a separate video part for each algorithm so that you can study it easier. So we are going to stop now and start with insertion sort. We start with insertion sort. Now, as I said, we expect you to draw a diagram almost similar to the one on screen at the moment in the exam. You have to clearly explain the steps. So half of the marks will be for steps like this, and half of the marks will be like the diagram. But I want you not to memorize this. You need not use these steps. The idea is that you are able to write your own. Now, in today's video, I'm going to do something strange. I'm going to work in a presentation that is not running, so please bear with me. I'm going to show you how these numbers are sorted. So what I want you to imagine that there are students standing in front of the class, each with a number, a poster with a number within. And I'm going to move the students in order to sort the numbers. So the first student carries a board with a number 11. The second student carries another board with a number 6, 4, 12, until the final student has a 1. Now I'm going to first explain insertion sort this way, and then we will go to the more formal way of the book. But from experience, I think it's better to get the hang of it just in a normal way before we start. Insertion sort makes the assumption that the first item is in the list is sorted. So let's say the first item is sorted. And then the idea is to put the next item, the 6, in the list in its sorted position. Okay, but there's a trick. The problem is we need the space of the 6. So we are going to put this 6 out of the list, sort of on a hold position, which we call current element, and then we are going to say, okay, now the first two elements are sorted. Then we want to put the 6 in its right position in the sorted list. Now to achieve that, we are going to search from the back to find the right position. So we are going to compare the 6 with the 11. If the 11 is bigger than the 6, we are going to move this 11 on, one position on, and so that there's space for the 6 there. Okay, so what did we do? We moved the current element out of the list. Then we searched from the back of the list for the new position, and we moved everyone on to make space. Let's do it again. Okay, so the second iteration, by the way, we are now, the outer loop in the double for loop implementation is going from element to element to element. The inner loop is checking for the right place. So the outer loop is at position 0, 1, 2, which is this 4. You step ahead. Now you check, is this 11 bigger than the 4? Yes, so move it on. Is the 6 bigger than this 4? Yes, move it on. I can just grab it. And then the 4 can go into the list. At this stage, I always end when the list is finished, but it might not be the case. Okay, let's take the 12. So you move the 12, okay, step forward so that there's space in the list. Is 11 bigger than 12? No. So then 12 can just move back into the place, and it's sorted now. Okay, here's an interesting one. Let's take the 9. So this vertical bar indicates the sorted section of the list. Can you see? I move that all the time. Every time a new iteration in the outer loop is done. Get the 9 out of the place. Out of the place of other elements. Compare the 12 and the 9. Yes, the 12 is bigger, so I move it. So note how I search from the back. Is the 11 bigger than the 9? Yes. Move it. Is the 6 bigger than the 9? No. And then move the 9 into its place. Okay, so there are 3 options. Every one can be smaller than, like in the case of the 12, then you just move it back. It can be somewhere in the middle, like it was just in the 9. Then you move the 9 out of the way to be able to move the others back. Or it can be right at the beginning, as we had at the start, but let's do another one. So the outer loop has done a new iteration. Now the 2 moves out of the way, and every one we do now is the inner loop. Very important that you understand that the outer loop, if the outer loop's loop variable is a I, for instance, I start searching at I minus 1. That would be position I minus 1, that would be position I minus 2, I minus 3, and so forth. Okay, so 2 out of the way. You compare 2 with a 12, 12 is bigger, so 12 must move on. This is done with the inner loop. 2 compare with 11, 11 is bigger, move on. Compare 2 with a 9, 9 is bigger, move on. 2 with a 6, 6 is bigger, move on. 2 with a 4, 4 is bigger, move on. At this stage, my for loop will reach the end, and because all the numbers have been moved, and the 2 will go right at the beginning. Okay, let's continue this. Now, I'm not writing it, I'm showing it to you in a way that you cannot do in the exam. You can write every one a line by line, like in the textbook slides. We will get back there. This is just for you to really understand what's going on. So the 5. Insertion sort, what does it do? It assumes the part of the list is sorted and every new element is inserted in its correct position. But by doing so, you first move that element out of the way. So so that each original position in the array can be occupied by another position, by another element. So move from the test from the back. 12 is bigger than 5, move the 12. 11 is bigger than the 5, move the 11. 9 is bigger than the 5, move the 9. 6 is bigger than the 5, move the 6. 4 is not bigger than the 5, okay, so I can move the 5 in there. A final one, now which again is kind of a special case. Get the 13 out of the way so that the other can move up. Compare the one, the biggest one. Is 12 larger than 13? No, so the 13 can just move back in its place. And now, just to make myself a lot of work, I've put the 1 at the end, so 1 should step forward. Now, is 13 bigger than 1? Yes, it should move. 12 is bigger than 1? Yes, it should move. 11 is bigger than 1? Yes, it should move. 9 is bigger than 1? Yes, it should move. 6 should move. Do you know why 5 is moving? Yes, because and it's larger than 1. 4 is moving. 2 is moving, and now I'm at the end of the list, so my for loop searching will end, and now I insert the one there. Back at the slides of the textbook. Now you know exactly what is happening. Now you should try to figure out how this works and the arrows, because the arrows helps you to indeed answer your exam question. So you start with a list. This list will be given. You assume the first position is sorted. Now you add the first position 9 to the list. It's in its right position. Now you try to add the 5, but the 9 should move. You add the 4, but the 9 and the 5 should move. Can you see that this depiction, although there's nothing wrong with it, it's kind of not telling the whole story. It's not really helping you to understand the code. So I would want to see more than just these arrows in the exam for a full mark effort on explanation of insertion sort. If you still do not understand this diagram, first rewind and go a little bit back. Okay, a little bit of more detail. It gives you diagrams to show how it is sorted. Now, I have to say, if you don't understand insertion, perhaps I don't think this will help, but for those of you that just need a little bit more or different way of looking at it, it might be wonderful. The idea here is that the 2 is sorted, the grayish part of the list is sorted, and the orange part is the new one that's going to be inserted. And so the sequence is from this one to this one here. So now the 9 is in its position, now the 5 goes in, and the 4 is the next number, the 4 is in its position, the 8 needs to be sorted, and the 6. Now, this is not good enough for the exam to do it like this. I want to know more what is going on. Okay, they tell you a little bit more here, but I think we have done this. I want to go to the code. And the code, I hope, links more to what I have explained. The idea is that the outer loop, there's 2 loops, the inner loop and the outer loop. You get a list to sort. The outer loop is every time that a new element needs to find a place in the array. So the outer list starts at 1. Can you see it? Why 1? I think you know. Where does the list start? At 0, but the outer loop starts at a 1 there. Yes, you are right, because it assumes that the first element is sorted. So we are going to insert the ith element in its place. So we don't need to insert the first element in its place, it's already sorted. Now, in my depiction, I moved the ith element forward to make space, and this is here. Current element is the placeholder for that element. And now I'm searching with the inner loop, that's from K. I'm searching from position I minus 1. Yes, it's very hard to figure out right at the beginning. You need to picture this while you are halfway through it. So let's say I'm already using the fifth element, position 5. So now I'm searching from 4 to 0. So for K will go from 4, 3, 2. And remember, the for loop is like a while, so both must be true. K should be larger than 0, and list K should be larger than the current element. If any one of those are not true, this list will end. The problem with a for loop is K is always decremented every time the for loop iterates, but sometimes we forget that. In a while loop, we are reminded of it constantly. So can you see that this is what we have done? If the current element is the smallest, it will this K larger than 0 be, that will stop us. Otherwise, it will be list K larger than the current element. The moment you find one that's no longer larger, this loop will stop. And what is it doing inside the list? It is actually moving on. It is replacing element K plus 1 with K. Now, what you should see is we start at I minus 1. So if we want to insert number 5, and we do the moving on thing, it is K would start at 5, so K plus 1 would be list K. Can you see that was the place, the old place? K plus 1 is list I, list K plus 1. Since K starts at I minus 1, K plus 1 is equal to I the moment it starts. But only then for the first iteration, of course. So it replaces that element's position with its neighbor. That is why I made all the elements step forward, so that there's space for it. And this will continue until one of these conditions are true. Okay, and now I want to put the element in its place. Now the problem is, you need to understand about K plus 1. And the answer is here. The final time the for executed, K was decremented. So let's say this element was at the beginning of the list. K larger than 0 equal, now K is equal to 0. Yes, then K is decremented. K is now minus 1. Is it larger than 0? No, it's minus 1. But I cannot put something in position minus 1. I want to put it in position 0. Therefore, we have K plus 1 here. So this code is working 100% correct. I can tell you a little cheat if you could. Your practical is to make it work for the array list class, and there's one little cheat you need to know. You will have a Java error here. It will tell you K might not be initialized. And then just think carefully what is the initial value you can. It doesn't really matter because you're going to give it another value just at that stage. Okay, so that is insertion sort. So we are going to stop the video and make a separate video for each sorting algorithm. The second idea we are going to do, or the second algorithm, is bubble sort. You all know bubble sort from last semester. It's one of the first sorting algorithms you learn. But very few students actually know what bubble sort does. And I have to warn you, there might be, I think there's an error in the book's animation. where it sends you to the internet. There's some slides there where you go to the internet. Okay, so have a look, follow. We do the same way. So we take, first of all, we play a little bit with the students standing in front of the class. Can you see them holding their numbers? And then we go to the more formal ideas so you can understand what to answer in the exam. So bubble sort works with 2 for loops. The outer loops will take one iteration. At the end of the outer loop, you are guaranteed that the largest number is at the back of the list. Okay, how does it work? We compare neighbors and we switch them around if necessary. Compare the 11 with the 6. Which is the 11 bigger than the 6? Yes. If so, switch them around. There they are. Now, different from the book's animation. Compare the 11 with the 4. The 11 is bigger than the 4. Sorry, I should not change it. If the 11 is bigger than the 4, switch it, swap it. Compare now, which two are we going to compare? The 11 and the 12. Do we need to swap it? No. Do you know why? Now the 12 and the 9, should we swap that? I think so, because 12 is bigger than 9, so let's get this 12. Come on. 12, off you go, let's swap it. Can you see I'm taking it somewhere else to swap it? Yes, you know that in the temporary variable. Okay, 12 is bigger than 2, so you know why we swap it. Every time we use the inner loop to do the swap, and the outer loop is kind of getting the biggest one at the end. 12 and 5 needs to be swapped. 13 and 12 needs to be swapped. So, worst case scenario is it's going to take me n attempts or n swaps to get the biggest one. No, I just lied. Let's just move back. 12 and 13 should not be swapped. Are you awake? I'm awake or not. Okay, 11 and 13 should be swapped. Okay, I was saying that it's going to take, worst case, n swaps to get the largest one there. And how many numbers do we get to have to swap? N times. That's why we say n numbers and everyone can take n times. That's why we say it's almost n squared. Now you can know that it's not really n squared because the second n, it's n times, it's a summation where the inner loop gets less every time. The first time it takes n times, the second one n times minus 1, next one n minus 2, n minus 3. But if you follow the rules of asymptotic analysis and you compute everything, you still end up with n squared. Okay, so this second iteration. So I can, let me just see if I can manage this. So the first iteration will lead to that. Let's see if I can manage this. The second iteration, yes, it will. Okay, I can now start again. I know my last item is sorted. Is 6 larger than 4? Let me stay awake this time. 6 larger than 11? No, it's not. 11 and 9? Yes. 11 and 2? Yes. 11 and 5. Yes, can you still see I moved this part out of the way to swap it? I need the third variable when I swap two numbers. 11 and 12. No, I'm awake. Are you awake? 12 and 1, swap it. Okay, shall we do this trick again? So after the second iteration, I know now that the numbers are sorted up to the very last two. So now I can show you the next iteration, if I can get it working again. Yes, it worked. Okay, so I need not even copy those. Okay, the 406 shouldn't change. This is 4 larger than 6? No, it's not. Is 6 larger than 9? No, it's not. Is 9 larger than 2? Yes, it should swap. Is 9 larger than 5? Yes, it should swap. Is 9 larger than 11? Yes, it should swap. No, sorry about that. 9 just falls not larger than 11. I should be awake. Is 11 larger than 1? Yes, it should swap. This one, the board, the factor is getting the better of us. Okay, so do I have to continue until I'm done? No, I think I'm going to not do many errors. Out of boredom, let's do one more. So every line is the outer loop in the method, and the inner loop is the swapping. 4 larger than 6? No. Is 6 larger than 2? Swap it. Now you can go and look inside your array list class. There's a sort list which uses double sort. Is 6 larger than 5? Yes, swap it. Bubble sort is actually nice patterns, and you can have a look at a number of things. 6 not larger than 9? No. 9 larger than 1? Yes. Can you see a few nice things about bubble sort, because I'm tired now, that the end is sorted and the last one always stays last. So the rest of the list order remains almost the same. Every time the largest one is bubbled till the end. So the largest one is bubbled till the end. You can hear the bubbling sounds of my mouse when I swap these. The trick, of course, in the exam is to remember which method goes with which name. So remember that the idea is that you bubble the biggest one. So let's look at the formal way of representing this in the book's presentation. This is similar to what you can write in the exam. Here in the textbook code that show you how they compare and how they swap. So you should just make sure how you read it. You read it the 2 and the 9, compare, and then you swap it. You don't swap it because 9 is larger than 2. Then the 9 and the 5 is compared, then you swap it. The 9 and the 4 is compared, then you swap it. The 9 and the 8 is compared, then you swap it, and so forth. So you read first this. The first pass is to get the biggest one at the back. That is the first iteration of the outer loop. Then this is the second pass. Now, in my diagram, that was the second line I copied. And it moves now again the largest one to the back, and that is 8. And the third pass, and so forth. And here's the idea that it's the first one, so it's n minus 1, n minus 2, and so you can compute that, and with this, all of this done, you will also get to this formula, and that is still order n. Okay, to look at the code, let me just go to the next slide here. The idea is that the outer loop is the passes, the inner loop is to swap the elements, and when will it be swapped? If a number is larger than its neighbor, and you need a 10 to do that. So that is binary sort, bubble sort. So the important thing is in bubble sort is that you have to remember you bubble the largest element to the end. Now you will see in the MyArrayList class we've done in the previous study units that there is an implementation of that sort list in the array class. You will see that, of course, we cannot do this with generics here where the elements are compared. We will have to use compared to for that. Okay, so that ends our discussion on bubble sort. Merge sort is one of my favorite. I enjoy merge sort, but it's kind of hard to understand. But if you get the hang of it at first, then it's easy. It's luckily you know merging. So it's very important that you make the link between the merging of arrays linked list we have done previously and what we are doing now. That's exactly why we have done it. So the idea is you take your list and you divide it up into two sections, and every time you divide it up to two until you have only two elements to sort. So I'm going to divide it first. I'm going to say these 4 of rings. I started with 8, I know I'm cheating, but it's just to make things easier. Oh, there's a 9th one, let's just delete that one because it's going to give us problems. You can understand later on why it can stay there or not stay there, but for the moment, for your first understanding, let's get this as a power of 2. Okay, so we had 8 elements and we divided it into 2 groups of 2. This group in total is the body of this group. Okay, the second iteration we are going to divide it again into 2. I'm only going to work, now let me work with everything. I wanted to say I'm going to work with one of the sides, but it's better if I do it in full. If you get bored, then I'm sorry. So let's mark. I'm working with 2 lists from the beginning as if it's a fresh start. So I'm working with this as one list and that is another list. And I do exactly the same. You should see that this is kind of recursive. Okay, so I divide this list into 2, and now I have new buddies. It's very important to understand which are buddies. In the first iteration, these 4 together was the buddy of those 4. In this iteration, these 2 forms the buddy of those 2. Buddies are those that were once together and has been separated. I know it's not hard to do when you have a number of elements that's a power of 3, like 8. It becomes really interesting. This buddy thing is important when you don't have a number that is a power of 8. Okay, let's make a copy again. Now I have typically 4 lists, 1, 2, 3, 4 lists, and every list I'm going to divide again into 2. These 2 are now buddies. These 2 are buddies. I'm still dividing, I'm not sorting. I'm dividing my list up into sections by dividing it right in the middle, until every list is exactly 1 element big in size. And once I have that, I start by merging sublists. So each of these are sublists now. I have 8 sublists. And now I'm going to merge this with using the typical merging algorithm. Let me just make a copy of it. So let's merge these 2 buddies first. The So I'm going to merge buddies. I'm going to merge the 11 and the 6. And by merging it in a new list, I will indeed swap them. But let's do it the right way, the merging way. I will compare, I will have 2 pointers, one would be at 11, one would be at 6. I will take the smallest one and put it in position in the new list. And then I will take the other element, put it into position in the new list. So I will compare, let's do that again. We have 4 times to merge 2 baby lists. So let's merge these 2 baby lists, sublists. Have made 2 pointers, point at the 4, point at the 12, which is the smallest, take the 4 and then the 12. Now you should see that I indeed make them into one list. Let's just move these closer together because they are technically one list. Now, the same here. Have a pointer in this sublist, have a pointer in this sublist. Take the one with the smallest value, put it in the new list, and put the other one also in the new list. And do the same here. Now I have 4 sublists, and the idea is that I can merge the buddies. Which are buddies? Are this one and this one buddies? The 4 and the 12 and the 2 and the 9? No, they are not buddies. They've never been a single list that was divided. This list here, the 611 list, is the buddy of the 412 list. But let me first copy and move stuff so that I have more space. One day when you're rich and you're working for Microsoft, you can get Microsoft to create a PowerPoint tool where you can move during presentations objects. But for now, I'm cheating. Okay, so I'm merging this list and this list because they were buddies. Now I'm forming a new list. So I have 2 pointers. I have a pointer. I think we should actually get ourselves a pointer here. Let's get a shape. Let's make a arrow, and we have a pointer here and a pointer there, so that you can get the right idea of the merging that's taking place. So you have a pointer in your 2 subfields. You compare the 2 elements of the pointer, and the one that's smallest go to the new list, and the moment you do that, you move on the pointer. Compare the ones at the pointer. 6 is smaller. The moment you put it in the new list, move on the pointer. Compare the 2 at the pointers. Smallest one to the new list. Now the pointer is at the end of the list, and copy the remainder of the other list. And you still remember that's the algorithm for merge. Shall we quickly do this side as well? So we have 2 pointers, 1 pointer at the beginning of the list, each list. Compare the 2 numbers at the pointers. 2 is smaller than 5, so move 2 to the new list, move on the pointer. Now the pointer is at 9, compare the 9 and the 5, 5 smallest, move the pointer, compare the 9 and the 13, 9 is smallest, move the pointer, pointer falls out of the list, so stop that idea, take the longer list and move all the elements. Great, so let's do it the final time. Now I have 2 lists and I have to merge them, doing the 2 pointers. Compare the 2 numbers at the pointers. 2 is the smallest, move it and move on the pointer. Compare the 4 and the 5, 4 is the smallest, move it and move the pointer. Compare the 2 at the pointers, the 6 and the 5, 5 is the smallest, move it to the new list and move the pointer. Advance to the pointers, 6 and 9, 6 is the smallest and advance to the pointer. 11 and 9, 9 is the smallest. answer the pointer. 11 and 13. 11 is the smallest. Move it if I can grab it. And move the pointer. 12 and 13. 12 is the smallest. And the pointer will fall out of the list. And that means copy all the items from there. Cool. So can you see how we use the typical merging algorithm to sort? So what did we do? Just to recap, we took our list, long list, we divided it into two. Those two are buddies. Why is it important? Those are the two that will merge again later. Take each list divided into two. Those two are buddies. We will merge those again. Take each list divided by 2 until you have only a single element in the list. And then those two are buddies, merge them. These two are buddies, merge them. These two are buddies, merge them. These two are buddies, merge them. And I kind of did not make enough copies, but then the idea was that these two are then merged and so forth. So let's go to the book's example. So it's much more complete, but I think it is helpful to do it this way first. Let's see if you can follow this. Now remember, in the exam you have to draw the diagram and explain. So if you write down like this diagram, I'm sorry, only 3 of the 10 marks. You need to really explain what's going on. Now, I find it hard again from the book to understand because there's no indication that it's truly merged that's happening from each step to another. But it's a better presentation than mine, or a representation than mine, because it's neater, that's why I'm using it. So you have the numbers, now you split it in two lists. Now you split it in two lists, now you split it in lists. Now you start merging. You merge the 2 and the 9, you merge the 5 and the 4, you merge the 1 and the 8, you merge the 6 and the 7. And how you merge this is a buddy of that one. You are not merging the 4 and the 5 and the 1 and the 8 because they were never one, as you never split the list on them. Okay, so you merge, you have a point on the 2 and a point on the 4. Take the smallest one and advance to the pointer. So you have a 9 and a 4, take the smallest one, the 4, and advance to the pointer. Take the 9 and 4, the 5, compare, put the 5 in and advance the pointer, copy the rest of the numbers. But you have to make the mental link to the merging algorithm, and that is merge sort. Now, what you should see in terms of analysis, it's cool because it is a log. It is order the log something because we are splitting the list. So if we have 8 numbers in 3 levels, we have splitted the list, and in another 3 levels we have sorted the entire list. So it is 2 times log n to sort this, and that's order log n to sort it. But you have to add the merging as well, and the merging is order n to actually merge it. So if I can just go to the next slide. If you analyze it, you kind of have this log in plus the merge time. Okay, I disagree with them, so let's just stop the video here. What I want you to understand of merge sort, it is that it's recursive. You kind of merge the first half and the second half every time. You first divide the list, and then you divide it into 2 parts, and then you merge it. So you can kind of use the recursive algorithm for this. This diagram just explains more. They do an analysis here. They say it's easier if n is a power of 2 you split it into 2 subarrays and you sort it using the same algorithm recursively. And you can compute the time, and the final time is typically n over 2 plus n over 2 and plus order n. So it is one of those recursive analyses which we did not do. So we are going to move on to the next one in the next video clip called Quicksort. That's also a recursive one, but more on that just now. Quicksort is not for the faint-hearted. It's the most difficult one of all to understand, and every book explains Quicksort differently. It's also done with recursion, but this book's idea is kind of one of the easiest one to understand. So let's move me down, we will move me up again. Now, once again, I think it's easier to understand it if you think about students standing in front of class with boards. What's important is that we are going to have, again, 2 pointers. I'm going to move my 2 pointers here. Quicksort works with a pivot. Now there are various ways to select a pivot. Now this book chooses the first element as the pivot. Now I prefer to use a better method as a pivot. I'll talk about that later on. So let's say 11 is our pivot. Now the aim of Quicksort is to divide the list into 2 parts. With the one part, all the numbers smaller than the pivot, and the other part, all the numbers larger than the pivot. But how it is accomplished is very, very cool, and I want you to pay attention to that. Okay, so 11 is our pivot. Let's move our pivot a bit forward. Now we are going to have 2 pointers. There they are. Textbook calls them low and high. I'm going to test each of my pointers in every iteration. I'm going to say, is 6 smaller than 11? Yes, it is. Move on the pointer. Now I'm going to say, is 1 larger than 11? Remember, on the second side, we want all the elements larger than 11. No, it's not. Keep that pointer there. Okay. Is 4 smaller than 11? Yes. Move on the pointer. So that pointer is stationary until this pointer stops as well. Is 12 smaller than 11? No. So now we are going to take action. Okay. So now we are going to swap the 11 and the 1. And continue with the process. Is 1 smaller than 11? Yes, it is. Continue. Is 13 larger than 11? Yes, continue. Is 5 larger than 11? No. So stop that pointer. Is 9 smaller than 11? Yes, continue. Is 2 smaller than 11? Yes, continue. So, when these pointers meet one another, we know that we have the position of the 11. So I'm going to make a copy of what we have, and so that we can continue. I made everything a bit neater. So the basic thing to understand is that the first half are all smaller than 11, and the other half all bigger than 11. So now we have 2 lists. With 11 being in its final position, we normally create a new array, otherwise it's too much shifting. Okay, so 11 is in its position. That 11 will never move again. It's in its right place. Now, I can treat this part, the left part of the 11, as a list to be sorted, and the right part of the 11 as a list. So the right part is so small, it's going to be done quickly. So let's play around with the left part so that you can better understand Quicksort. Assume the first one is the pivot. Okay, so I want to get 6 in its right place with all the numbers on smaller than 6 on the one side and all the ones larger than 6 on the other side. Note they won't be short. They will just be smaller than 6 and larger than 6. So I use 2 pointers. Is 4 smaller than 6? Yes. Move on. Is 5 larger than 6? No, it's not. Come this side. Is 1 smaller than 6? Yes, it is. Is 9 smaller than 6? No. So now I can swap these two. Is 5 smaller than 6? Yes, it is. Is 2 smaller than 6? Yes. Is 9 smaller than 6? Yes, it is. If I just neaten up, and now, bang, my pointer is moved, and I have the position of 6. Okay, this side, 11 is the pivot, is 12 smaller than my pointers will meet immediately because they will both be at the same position, and the simple compare will be done to put the pivot in its correct position. So the pivot will go into its right place with a simple final compare. Okay, so let's move on. We will put, where should the 6 go? There after the 2, where my pointers meet. Let me just tidy up a bit. I can create a 2 list with the pivots in its position. The other list is has only one element, so it is sorted so that 9 is also kind of in its position. Now we have to use Quicksort to sort this small list. What will happen? 4 will be our pivot. Okay, and now I will divide the list in such a way that all the numbers on the left side is smaller than the pivot and all to the right is bigger than the pivot. So is 1 smaller than the pivot 4? Yes, it is. Move. Is a 5? Wait, it's not. It's 2 larger than the pivot. No, it's not. So I'm going to swap the 2 and the 5 around. And then I'm going to move my pointers, and there my pointers meet. And the moment my pointers meet, I know I have the position of the pivot. So I can put this pivot right here in the middle. Okay. So my pivot 4 is in the right place. I've divided my list. Now from that iteration 6 was in its right place. The pivot 9, the single element list is sorted. 5 is another single element list, it is sorted. The 4 is in its right place. I only have 2 elements, one would be the pivot, and then I can compare it and so forth. That list is sorted. Quicksort always check to see how many elements you find the list so that you can stop at the right place. What you should see is a recursion. If we quickly recap, you take the first element to be the pivot, and then you run with 2 pointers through your list, one from the beginning, one from the end, and stop when you find an element. If you start at the right side, that is bigger, that's not bigger than the pivot, you stop. From the left side, compare each to the pivot, you stop when you find one that is not smaller than the pivot, and you swap them. At the first time we swap this 1 and the 12, if you remember correctly. Let's go to the book slide, see there. You will see exactly the same idea in the textbook. They use the first one as the pivot, then they start searching and they swap everything so that it is the one part is all bigger than the pivot and the other smaller, but once again they don't tell you exactly how it is done. It is done with the 2 pointers. So if we add some idea to it, I can grab my pen. Is 7 bigger than 5? Yes, sorry. Is the 7 bigger than the 5? Yes, it is. So the pointer will move on. Is the 6 bigger than the 5? Yes. Is the 1 bigger than the 5? No. From that side is the 5, the 2 smaller than? Yes, it is. And then the 9 and the 1 will swap. There you can see the 1 and the 9 swap. So although this diagram is true, it does not explain how it is done. Now here they give more detail of exactly how it is done. So all of this only shows the first iteration. Then the pivot is in the middle. And then you have to do everything again. So when you do this in the exam, you need to explain. Okay. Quicksort is a very quick. It's the quickest one. If you look at it, but we have not done a recursive methods, but it's order in log in if you analyze it. Okay, so our final one is bucket sort. So we are going to finally have a look at bucket sort, and then you know all the sorting algorithm. Let's focus on bucket sort. You have done bucket sort in study unit 2. Now you will remember that it works for very special cases. It works when you have a relative repetitive list of integers. First you create an array of buckets. Now, but to start bucket sort, you also give not only the list, but you give the largest number to the algorithm. So in this case, the largest number is that 4. And so that's the algorithm does not find the largest number, it is given to it. So you create buckets from 0 up to 4. This is now an array, and you initialize each one of them. Okay. Now to show you this without drawing is a bit hard, so I'm going to play this PowerPoint so that I can hopefully draw with my pen. Okay, and then I'll go back again. So the first step is to take every value of the array and link it to the index of a bucket, and you are going to increment that item. Okay, there's something you can do that's wrong, but I'll talk about that later. You take the second one, you take the value of the item as the index of the bucket and you increment it. You take the value as the index of the bucket and you increment it. Value becomes index and you increment it. Value becomes index and you increment it. Value becomes index and you increment. 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 Okay, what you should see is with one pass, you have all those buckets filled with the right numbers. I did not search for all the ones and said 1, 2, 3, 4 ones, go and write a 1 there. Then search for all the 2s. That would not have been done in one pass. But by doing it the way I did, I actually, in one pass of this list, I knew everything about the buckets I wrote down there. So please note the difference. In the exam, you must have evidence that you know this. Okay, so this is now half the job done. Okay, so now I'm going to grab my keyboard, go back to editing mode to be able to do this. Oh no, let's just write. Okay, so now how do I sort? I read the bucket. I say I'm going to write 0 zeros. Then I continue. I'm going to write 4 ones. 1, 2, 3, 4 ones. You have to find a way to indicate that you know this. I think you can say 4 times 1. 1 times, was it? Sorry, not a 1. Yes, it was. The 2 was 3 times. You can circle those. 3 times 2. 2, 2, 2. 1 times 3. And 1 times 4. And there's your list sorted. Isn't it amazing? Now, this thing I've done here, 3 times 2, actually was a inner loop. I've visited each bucket, that's the outer loop, but the inner loop. So, but it's not really n square. It is n plus m, because the inner loop is not in the worst, the total items of all the inner loops combined is m times, and not n squared times, if that makes sense. But there's another video on study unit 2 when we did complexity, when this was done. So bucket sort is kind of easy to know, but it's kind of hard to explain. So if you do this in the exam, you really need to write in words what you are doing. Otherwise you won't get your marks. And let me say this carefully. If this question is 10 marks, explain in your own words with the aid of a diagram how bucket sort will sort these numbers. You will get 3 for what you see now on screen. The other 7 is for your explanation of what happened. So be careful, use the correct terms. Use the term index. Take the value in the array, use it as the index of the bucket. Increment the bucket's value. Hope this helps. Let's quickly go and see if the book helps us. The book gives a discussion of it. It tells you a little bit of the analysis. It tells you the order n log n is almost the quickest, but these radix or bucket sorts might be slightly quicker, but they are so much dependent on the value, so it's so hard to really use them. Here they tell you a little bit of how it works, but it's not that helpful. You really have to go and search for, or sit down and create your own diagram to explain bucket sort. But you have 2 now. Have this video and the video from study unit 2 on bucket sort. Okay, can you sort now? Do you know which diagram fits which algorithm? Do you know insertion, bubble, merge, quick? Yes, quite a mouthful. Make sure you know which name goes with what. Take the effort to study this. I tell you now in the exam, what is expected from you is to create a diagram that shows how a specific algorithm will sort a specific number of items. Diagram only 3 marks. The explanation counts the most marks. You have to clearly explain what is going on. The more detail, for example, in insertion, you have to demonstrate for full marks that you know that the element I will be inserted in its correct position, but I needs to first move out of place so that the others can move into that position. Carefully plan this. If you want to score full marks, do a thorough job. Then you have to explain it in the exam as if you were explaining it to somebody that doesn't understand it. Okay, that's it for the study unit on sorting.